So we're continuing section 9.2, which is more about vectors. So we had just done the component of u along v, and now we're going to talk about the projection of u along v. So it's written, well, I'll write it up. Projection of vector u along vector v. So what we want is to have, here I'll draw it. If I have a vector u, and it's not necessarily horizontal or vertical, and I want to project it along a vector v, which is not necessarily horizontal or vertical, so vector v. So it's like I have an x and y component, except it's not an x horizontal and a y vertical. It's an along v component, and then later we're going to have the other one. So what I want is the component along v, but as a vector, so it's called a projection. So it'd be perpendicular like this. So I want the vector that's along v, and it forms a right triangle with the terminal point of vector u, just like it does when we have the horizontal axis and the vertical axis, and we have the horizontal component and the vertical component. So this here in red is the projection of u along v. So now let's figure out how to find it. So algebraically, the projection of u along v would be the component. Remember that the component is a scalar of u along v multiplied by a unit vector in the direction of v. Because the component of u along v is the scalar measurement, so the length of this section that's along the v direction. So we already know how to do that. And then if we take a unit vector, so that would make it a vector. This is a scalar, this is a vector. So unit vector, so length 1, along v, so that will get the direction part of the vector. So now let's simplify that to be an expression that we know how to evaluate. So remember that the component of u along v is u dot v over magnitude of v. So that's this part. And then a unit vector is the vector divided by its magnitude. And then if we simplify this, the denominator is magnitude of v times itself. And I didn't change the numerator. So that's squared, and it's multiplied by v. I shouldn't put a dot because it's not a dot product, because that's a scalar and that's a vector. So this is the projection of u along v, and we don't have to derive it again because now we have it. Another thing we might want to do is resolve a vector u into the sum of two vectors, u sub 1, which is parallel to v, and u sub 2, which is perpendicular to v, or orthogonal. So if you go back to the diagram, a component that's parallel and a component that's perpendicular. So just like when we have the x component and the y component, we're having an along v component and a perpendicular to v component. So how are we going to do that? So first, let's say, remember that we want to have it be the sum of u sub 1 plus u sub 2, much like a vector is the sum of a sub 1 plus a sub 2. Therefore, if we let u sub 1 be the projection of u along v, which we just talked about, And then we want this one. So if these two vectors add up to u, that would mean, so I have this, u equals u sub 1 plus u sub 2. Therefore, u sub 2 would be u minus u sub 1, which is the projection of u along v. So u sub 2 is u minus the projection of u along v. So now we can use these. So those are other useful facts. So here's our example. If I have u a vector negative 2, 9, and v a vector negative 1, 2, and I want to first find the projection of u along v. So let's do that. So if I use this formula that we worked out from scratch, u dot v divided by magnitude of v squared all times v. So u dot v, so that'd be negative 2, 9 dot negative 1, 2 all over the magnitude of v. So I'm going to write that formula out. So that would be the horizontal component squared plus the vertical component squared multiplied by the vector v. So v is negative 1, 2. So now I'm ready to work this out. So I'm going to do the dot product here. So negative 2 times negative 1 is 2, plus 9 times 2 is 18. And then the denominator, so that would be I used the wrong vector in the denominator. This was supposed to be v, so I better fix that. Sorry about that. Might as well fix it right here. That was supposed to be v, and I accidentally put u in there. So it's negative 1 squared plus 2 squared. Okay, so the denominator here is going to be 1 plus 4, so that's going to be the square root of 5. And then I'm going to multiply it by the vector negative 1, 2. So now I have 20 over the square root of 5 multiplied by the vector negative 1, 2. And this was squared up here in the formula, so this was squared. So this is 5. So this gives us 4 times the vector negative 1, 2. So scalar times vector. So that gives us the vector negative 4, 8. So now we're going to go on to the second part of this, but we're going to come back to that answer and do a little reality check there. So part B of this example is to resolve the same vector u into u sub 1 and u sub 2, where u sub 1 is parallel to v and u sub 2 is perpendicular to v. So we already found u sub 1. That was the projection of u onto v. So u sub 1 is negative 4, 8. So now we need to find u sub 2. So remember, u sub 2 was u minus u sub 1. So u in the example was negative 2, 9, and u sub 1 we just found is negative 4, 8. So this is simple vector subtraction. So we find out that u sub 2, negative 2 minus negative 4, so that's 2. 9 minus 8, so that's 1. So my vectors, we have them, but let's write this out. So vector u is u sub 1, which is negative 4, 8, plus u sub 2, which is 2, 1. Now let's have a look at what we just found here. So let's do a quick little diagram. So if I make a rough sketch. So remember, my original vector u was negative 4, 8. So negative 4, 8. So that's 8. So it looks like this. So that's u if I put the initial point at the origin. And now let's plot u sub 1 and u sub 2 and see if they look like what we expect. Oh, I just plotted u sub 1. That's okay. We need u sub 1 anyway. U sub 1 was negative 4, 8. U sub 2 is 2, 1. So we'll do that one in a different color. So 2, 1. Let's place it at the origin. So that's u sub 2. So I have u sub 1 and u sub 2. What I didn't plot yet was my original u, which was negative 2, 9. So negative 2, 9 is here, or the terminal point is there. So if I go like this, if I've done this correctly, I will have this in component form. So let's see, this is u, and v was negative 1, 2. Need a third color. Negative 1, 2. Negative 1, 2. So that's v. So is u sub 1 along v? Well, it definitely is. And then is u sub 2 perpendicular to v? You can visually see that it is. And are u sub 1 and u sub 2 the vectors that sum to u? And remember our parallelogram method of finding the sum? So let's see if this is approximately a parallelogram. So if I do this a little bit off because I didn't use a graph, but you can see that this is a parallelogram. So that works. So that's great. So we have a reality check. All right, now we're going to move on to work, which is also a vector concept. So work is force times distance. So it's a measure of how much work it takes when you have to exert a force to move an object through a certain distance. So if we measure force in pounds and distance in feet, then the units of work in the English metric system, but not in the English system, but not metric system, are going to be foot, so it's pounds times feet, so foot, pounds. So let's do an example first with a simple example where we don't really need to use vectors. So how much work to lift a 20-pound object 6 feet off the ground? So I have an object on the ground and I'm lifting it straight up, so the force is going in the same distance as the motion, which we'll get to in a minute. So I literally am going to find the force by taking, find the work by taking the force and multiplying it by the distance that it traveled. So the force is the pounds, so that's the 20-pound object, and the distance it traveled was 6 feet. So that's 120 foot-pounds. Okay, pretty simple. Now they get more complicated. So what if the force is exerted and it's not in the direction of the movement? So let's look at this. So let's say I'm moving something from point P to point Q. So I'm moving this way. So this is the direction of motion. But I have a force that's going in a different direction. So this is my force. And I'm heading toward a point R there with my force. Then I have an angle between the line along which the distance is being traveled and the force vector. And I can draw up a perpendicular, just like we often do. And based on all of the calculations that we've done before, we can see that the magnitude of the force times the cosine of theta would give me this adjacent side, so parallel to the direction of motion. So this is going to be the component of the force along the direction of motion, which is the only thing we need, because only the part of the force that's moving, that's pushing or pulling or whatever along the direction of motion is going to actually move the object, and any force that's moving that way is not moving it in this direction. So a different notation would be the same one we've been using, and remember, components are scalars. So component of force along the direction of movement, and its magnitude of the force times the cosine of theta, which is also going to be equal to work. And remember that we also know, that's the force. So work is equal to force times distance. So I have the force, magnitude of force, times cosine of theta, so that's the force, times the distance, so whatever the distance vector is, it's going to be the magnitude of distance. So a simpler expression for this would be to put the two magnitudes next to each other. So this is the one to remember. Work is magnitude of force times magnitude of distance times cosine of theta. And you might recognize this expression from earlier in this very same unit. So it is exactly the dot product of F and D. Also useful. So depending on what you have, you might use one or the other of those. So keep those next to you while we do the next problem. A force, and here's the force vector, moves an object from, and I'm going to call this point P, 1, 3, to, I'm going to call this point Q, just so I can keep track of it, 5, 9, and we want to find the work that was done. So I don't have to draw it to do the calculation, but sometimes it's helpful to get a visual. So if I do a quick sketch of it, my point P is at 1, 3, and my point Q is at 5, 9. So that is my force. Oh, sorry, that is my distance. That's my distance from P to Q. D for distance. And then I have a force. That's the vector 2, 3. So I'm going to put that down here, even though it's moving along this line. So vector 2, 3. So that's my force. It does look like they're parallel, and in fact they are. But even if we don't know that, we can use our formula. So here we go. We're going to use our formula. So work equals the force vector dotted with the distance vector. So I can write it as the magnitude of the force times the magnitude Actually, there's two ways to do it, and I just started doing it the longer way that we don't need to do. So we're just going to do the dot product. So the force vector is the vector 2, 3. We don't have the distance vector exactly. We could work it out by kind of counting things out on our graph. Or remember the vector that connects these two. We would take the Q and subtract the P, Q, P. And that would give us 4, 6. So that's this vector, and it is exactly this vector. But really, you're picturing it starting at the origin, right? So that's why we subtracted these, and that kind of moves it back over here to the origin. So it's going to be dotted with the vector 4, 6. So when we do that, we get 2 times 4 plus 3 times 6. So that's 8 plus 18. So that's 26. And we're done. And the units are, we didn't have any units. So that is the answer. So that is our work. All right, great. The next one actually has a story, so it's more interesting. So here we go with the next one. Last one, the last one. So here's an example. A woman pulls a wagon horizontally by exerting a 20-pound force on the handle. The handle makes a 60-degree angle with the horizontal. Find the work to move the wagon 100 feet. So, person's walking along the ground, the woman's walking along the ground, she's pulling a wagon, the wagon has a handle, the angle between the handle and horizontal is 60 degrees, and we're going to move a distance of 100 feet. So the force is being exerted along the handle, so that's where the force is, and the distance vector is going this way parallel to the ground. So we want to use one of the two expressions for work. So if we do the dot product, we would need a vector for both of them, which we could figure out. But we have other information, so let's try using this one, where it's the magnitude of the force times the magnitude of the distance times the cosine of theta. And remember, theta is the angle between the two vectors. And since the distance vector is parallel to the ground, and the force vector is along the handle of the wagon, the angle between them is the 60-degree angle. So since we know that theta is 60 degrees, and the magnitude of the force is the strength or the length of the force, so that's 20 pounds. So we know that the magnitude of the force is 20 pounds. And the magnitude of the distance, that's just how far it is. So how far is the distance? There it is. So that's 100 feet. So it's actually relatively simple. So the work is going to be equal to 20 pounds times 100 feet times cosine of 60 degrees. So that would be 20 times 100 times cosine of 60 is a half. So that works out to be 1,000 foot